Good afternoon, everyone. I'm Monica. Today I'm going to give a presentation on natural language processing and network representation learning, looking at some algorithms and applications in the two research areas. So first, a quick look at the agenda of today's presentation. So I will start my talk by briefly talking about natural language processing and one of its famous algorithm, word-to-vec, and look at some of the applications of natural language processing very briefly. The focus of the talk is on network representation learning. It's also known as network embedding. I will be talking about how natural language processing was inspired network representation learning, and why do we need to use networks, the graphs, and what is network representation learning, and how did network representation learning originate from natural language processing, and how do we use network representation learning. After that, I will be talking about the network embedding techniques for four different types of networks, which are static homogeneous network, dynamic homogeneous network, static heterogeneous network, as well as dynamic heterogeneous networks, some algorithms and application there. And in the end, I will conclude the presentation by discussing some possible future directions in the research area. Okay, so let's start. So natural language processing, one of the most famous algorithms in NLP is word-to-vec. As the name implies, word-to-vec represents each distinct word with a particular list of numbers called embedding vector. So you can think of this as a set of numbers as XY coordinates if we are dealing in a two-dimensional space. But when we are actually using word-to-vec, we can set the number of dimensions to 20, 50, whatever number you need to set it. The quality of these vector representations is measured in a word similarity task. So this is one thing shared by natural language processing and network representation learning, that after we obtain the embedding vectors, often we cannot directly assess the quality, the accuracy of those embedding vectors. Instead, we use some proxy task to assess the quality of the vectors. And for the algorithm word-to-vec, the task was word similarity. In the word-to-vec algorithm, the vectors are chosen carefully such that they capture the semantic and the syntactic features of words. As such, a very simple mathematical function, cosine similarity, was used to measure the level of semantic similarities between the words represented by those embedding vectors. So a simple example is that, France and England, they are both European countries, and the vector representations of France is close to England in our embedding space. The word-to-vec algorithm proposed two novel model architectures for computing continuous vector representations of words from very large data sets. So data sets of up to billions or even trillions of words in it. And they use some text input data, such as you can think as Wikipedia text data or Google corpus text data. The two main performance metrics used in the word-to-vec algorithm is the accuracy and the computational cost. So for accuracy, we want to be able to learn the embedding vectors of words as accurate as possible. In the meantime, we want to do that in a lower computational cost. So if we are processing input text data of trillions of words or billions of words, we want to be able to generates the embedding vectors of those words within a couple of hours instead of a couple of days or even weeks. So the accuracy and the computational efficiency are the two performance metrics we care a lot about. And just briefly look at the two model architectures proposed in Word2Vec. So the left-hand side is the CBOW, continuous bag of words model. It predicts the current word based on the context word. And they also proposed a second model architecture called skipgram, and it's called continuous skipgram model. It's kind of the opposite of continuous bag of words model. It predicts the surrounding words given the current word. And then later, when I talk about network representation learning, we will see that this skipgram model architecture is used in network representation learning as well. So there are also some other state-of-the-art natural language processing algorithms such as Transformer and BERT, and they're helping a lot of NLP applications such as sentiment analysis. I've seen a lot of companies, data mining and text mining companies do that. And also applications include paraphrase detection and open source software network. So some researchers in the software engineering area, the software developers, they actually use natural language processing algorithm to analyze open source software network, such as GitHub, to analyze the, the commits a developer has made in GitHub, the software project they have worked on to find out their expertise, like a software development expertise. The other applications include machine translation, information retrieval, question answering system. And there's a more another application which could be more relevant to Dell, and it was pointed to me by Kim, which was published in this year's AAAI conference. In this work, they present a novel method by using natural language processing to automate the process of systematically identifying the key interlinkages between climate action and the United Nations Sustainable Development Goals from a large amount of climate literature. So here the input for their selected NLP method is a large amount of climate literature. So now moving on to the next topic, from NLP to network representation learning. So first of all, why do we use networks? So networks is sometimes known as graphs as well. It's a general language for describing complex systems of interacting entities. So if we look at this very simple network graph example here, we can see that in this graph, we have different objects represented by the circles. In graph, they're also called nodes. And we have different relationships between the objects. And in graph, we call them edges. So very often, networks, graphs, objects, nodes, relationships, and edges, they can be used interchangeably. And there's a subfield in computer science and mathematics. They focus on graph theory to analyze this this kind of data type. And a lot of real-world scenarios, they can be modeled as graphs of networks. So for example, our society is a collection of more than 7 billion people. And each people, we can model them as an object, and the relationships between different people, they can be modeled as edges in our graph. And also we would have communication system linking different electronic devices, interactions between genes and protein, which regulate our life. And even our brain, we can model the different neurons in our brain and the relationship between these different neurons in our brain as a graph as well. so what is network representation learning, network embedding, and how did this originate from NLP? So network embedding generates the no-dimensional embedding vector of an object according to the relationships that the object has with others in the given network. It originated from NLP techniques and based on Euclidean geometry. So you may have, till now, you may have realized some like similarities between network representation learning and natural language processing. For network embedding, we are generating the embedding vectors of the object given the relationship it has with other objects in the network. But when it comes to natural language processing, we're generating the embedding vectors of words given this word's relationship with other words, whether they appear in the same sentence or whether they appear in the same graph or even a same document. So there are some similarities or shared ideas between these two research areas. So basically, in the context of natural NLP, if two words often appear in the same sentence, then the embedding vectors generated for the two words tend to be closer with each other in the Euclidean space. And for network representation learning, if we construct academic collaboration, including different academics, and if they have collaborated together or if they have published a paper together, then there's an edge between these two academics. Then the embedding vectors generated for these two academics who have published together tend to be closer than others in the Euclidean space. So that's like the similar ideas shared across the two research areas. And here is a more visualized example of what is network representation learning. So in this figure here, on the left part, you can see we have input graph, an input network. And after analyze it using network representation learning techniques, we can generate the embedding vectors of them and map them into a two-dimensional space. So they kind of work like coordinates in this embedding space. And as you can see that in this input graph network, the red objects, they are collected closer than, if you look at one red object and one blue object. And after we mapping them into the embedding space, it's actually the collection relationship in the original graph have actually been preserved in the embedding space as well. So that's like the high level of what is network representation learning. And if we look at, so there are some similarities between NLP and network representation learning. Of course, there are some differences. So if we look at the difference by looking at three aspects: input. So obviously, NLP, you take a large text input data, training data. But for network representation learning, you are given a constructed network based on your problem domain. And some of the techniques, they both use scale-ground architectures, which I'll talk about more in details later. And the output, NLP gives us the embedding vector of a word, but the network embedding generates the embedding vector of an object in the network. So how is network embedding used? So basically, the generated object embedding vectors can be direct input for various downstream machine learning tasks. For example, clustering, classification, similarity search, prediction, or recommendation. So some people would also think these different kinds of downstream machine learning tasks, they are the application of network representation learning techniques, because you need to input those vectors into some task to have some final results. The other point is that also a lot of real-world application systems have used network representation learning in the domain of cybersecurity, biological medicine, e-commerce, and so on. Just a little bit like a few more examples of how the network embedding is used. So basically, given this input network, you know that you have the objects and the relationships, that you know that some of these nodes, they belong to the green class and some of them belong to the red class. Then you can generate, given this all, by analyzing this network, you can get the embedding vectors of each object and input that vectors into regression classification algorithm. Then they will the classification algorithm will tell you what this question marked object nodes belong, which class do they belong to. This is another example which is very similar to the previous example. So basically, you are given this and you can input the embedding vectors into each prediction algorithm, and the algorithm outcome can tell you whether there will exist an edge between those two objects. Okay, so after talking about the kind of relationship between network representation learning and natural language processing, I'd like to move on to the representation learning techniques for different types of networks. So the first one is for the static homogeneous network. So basically, this is kind of the most simple type of network among the 4 types of networks. So here is a simple example. So one is homogeneous network. That means we are only considering one type of objects and one type of relationships, and that's all. So basically, we have all this the 5 academics. The edges exist between them, represent the collaboration publication relationship. And the static means we only consider the network at a particular point of time, and it's static. It remains unchanged. And node-to-vec is one of the algorithms that was developed for this type of network. It allows the user to map nodes in a graph to an embedding space. The algorithm tries to preserve the initial structure within the original graph. So here is kind of similar to the idea in word2vec, where we want to preserve the semantic and syntactic features of each word in our input text data, training data. For the 3 aspects I mentioned earlier, we can just look at them more specifically here. So the input of node2vec is a graph, and extracted a set of guided random walks from the given graph. And the input of word2vec is Google News corpus. And these 2 algorithms, they both use skip-gram model. So for word2vec, the skip-gram model works on words and sentences. But when it comes to static homogeneous network representation learning, each node in the guided random walk can be represented as a word, and the entire word can be represented as a sentence in the context of NLP. And the output is fairly obvious. The result of node2vec is embedding vector of the object, where in word2vec is embedding vector of word. There have been quite a number of applications of node2vec in the areas of biological network analysis, drug discovery and development, healthcare, even COVID-19 misinformation. So now, moving on to the second type of network, which is dynamic homogeneous network. So I think it's pretty obvious that we are still considering only single-typed object and the relationships in the network. But this time, instead of considering the network at one particular time step, we are considering the network over the changes in the network over a period of time. That's why we call it dynamic. So basically, for example, this static network here happened at time step t, and imagine we would have this network at time step t+1, and from t to T+1, academic A3 and A5 might have developed some collaboration and they have published the paper together, then each will exist between them, A3 and A5 at time step T+1. And also, maybe from T to T+1, A4 decided that I want to go to industry, I don't want to stay in academic anymore. The A4 may even disappear from the network at time step T+1. So basically, when it comes to dynamic homogeneous network, we have to consider the changes happened over the period of time. And one of the algorithms have been developed for this type of network representation, network embedding. It's called dynamic triad. It was published in the 2018 AAAI conference. Then moving on to the third type of network, which is the static heterogeneous network. So basically, this time we're back to static again. We don't consider changes. We only consider the network at one point of time. But this time, homogeneous changes to heterogeneous. That means we are no longer considering only single-typed objects and relationships. We are considering multiple typed objects and relationships. So since it's getting more and more complex when we change the network type. So if we look at this figure here, it's an example. So in addition to academic as the first object type, we also have two other object types, which is the paper and the publication venue. And in addition to the publication relationship denoted by the black solid lines, we also have published relationship between an academic and a paper represented by the red dashed lines. And also we have the published at relationship between a paper and a conference represented by the green dotted lines. So now we need to consider multiple types of objects and the multiple types of relationships among those multiple types of objects. So basically, this is a very simple example to illustrate this type of network. But when it models some other real-world application domain, this kind of networks can get very complex as well. And some famous algorithms developed for this type of network are HNE and MetaPath2Vec++. Then we come to the last type of the network, which is dynamic heterogeneous network, which means the network contains multiple types of objects and relationships. And in the meantime, it changes over the period of time. So basically, most existing research, network representation learning, they focused on the first three types of networks. But starting from 2019, there have been increasing number of researchers working on, network embedding for dynamic heterogeneous networks, because very often the real world networks, they contain more than one type of object and relationships, and they do change over time. So that's why the network embedding in dynamic heterogeneous network have become received more attention in the past 2-3 years. And I was one of them. So I developed a novel representation learning method named Change2Vec, which considers a dynamic heterogeneous network as snapshots of networks with different time steps. And instead of processing the whole network at each time step, the algorithm models only the structure changes between the snapshots in the dynamic network. So there are in total 4 steps in the algorithm. At the initial time step, Change2Vec generates the embedding vectors of all the nodes in the network using the MetaPath2Vec++ algorithm. Then in the step 2, between 2 consecutive snapshots, we capture all the nodes that have been involved in structure changes. The structure changes were defined as newly added and deleted nodes with their one-hop neighbor nodes, as well as newly formed or deleted edges that caused triad closure or open process. So a triad is actually a fundamental of a graph, and it can be closed or open. And in a closed triad, there exists a relationship between any two objects, whereas in an open triad, there are only two edges indicating that two nodes in the triad do not form a relationship. And in order to preserve the heterogeneity feature of the dynamic heterogeneous network, specific meta paths were derived and followed in order to model the triad open and closure processes. And in the third step, we derive the embedding vectors for each node involved in the structure changes. And in the last step, we integrate newly derived vectors with unchanged vectors. And by doing that, we can get the up-to-date embedding vectors of all the objects at one particular time step. So some key details of the developed method algorithm is that first, the algorithm presumes network heterogeneous features accurately. So the common objective function of network embedding method is to maximize a given network probability in terms of the neighborhood relationship of nodes. Given a heterogeneous network G of all the nodes denoted as V, or the edges denoted as E, and all the types denoted as T at each time step, we use this objective function to maximize the probability of the given network. And this part here is a conditional probability of having a context node giving a particular load. And it's commonly defined as a softmax function. And the softmax function is formulated as this in this formula. In the algorithm, we also use stochastic gradient design to maximize the objective function for our algorithm. And in order to further improve the efficiency of the algorithm, I used heterogeneous negative sampling. The second key detail of the algorithm is it processes the network dynamic features efficiently. So in general, according to previous literatures, network usually evolves smoothly over time rather than it reconstructs itself between each time step. So therefore, we only derive the embedding vectors of nodes involved in structure changes at each time step, instead of processing all the nodes at each time step. Therefore, so this is the intuition behind the efficiency increase of the algorithm. So we evaluated the algorithm, the two important performance metrics, efficiency and accuracy. We used clustering as a proxy task to evaluate the accuracy of the node embedding vectors. The ground truth information we used were retrieved from Google Scholar based on 8 different computer science research categories. And we compared with, at that time, the state of the ART algorithms, dynamic triad and metapath to VIC, and the performance metrics we focused on were the embedding vector accuracy and the efficiency, the runtime of the methods. So, these are some results of the experiments. So basically, the change to VEC algorithm achieved very compatible embedding vector accuracy. In terms of efficiency, dynamic triad was the one who consistently outperformed others. But the thing is, dynamic triad is a representation learning technique for dynamic homogeneous network, which means the algorithm treats different types of objects and different types of relationships in the given network as one type. And the price it pays is that the accuracy, the embedding accuracy generated by dynamic triad was very low. So so this is the trade-off between efficiency and accuracy. So because the NMI stands for normalized mutual information, and it's in between 0 to 1. So the higher the number is, the more accurate the embedding vectors we've got. So if we look at some numbers got by dynamic triad, it's very low. It's 0.1, 0.3 as compared to 0.7 or 8. So that's like the trade-off for efficiency. And we also used another evaluation metric called the ARI, Adjusted Rand Index, to evaluate the results, just to show that different metrics confirm the results. So we've obtained very similar experiment results. So to conclude this presentation, so the focus is on the network representation learning, and at the moment, still a lot happening for the network embedding techniques. From my point of view, and also some recent literature paper, people discuss what are the possible future directions for the area. First is definitely about dynamic and scalability. So if we are doing representation learning in big data or even streaming data, how can we process everything? So at the moment, I'm using some statistic bound to say whether we can model the distribution changes in the network, and whether we can just get the up-to-date embedding vectors from the latest data and forget about the old data in the streaming environment. And also there's a possible direction is on the interpretability of the learned embedding vectors, which kind of leads to the second point, apply and adapt network representation learning techniques to their application domains. Because if we do have a good domain, then we can increase the interpretability of the learned embedding vectors for sure. So that's pretty much of my talk. Thank you.